Ladies and gentlemen, please be seated and welcome all our Kavli Prize Laureates, the chairman of the Kavli Foundation, and the president of the Norwegian Academy of Science and Letters. Ladies and gentlemen, please all rise for His Majesty, the King of Norway. Please welcome on stage Selda Ekiz and Jim Al-Khalili.
Yes, we are. Your Majesty, Your Excellencies, Prize Laureates, ladies and gentlemen, it's a pleasure to welcome you all to this wonderful ceremony celebrating the Kavli Prizes in nanoscience, astrophysics, neuroscience, the smallest, the largest, and the most complex.
The Kavli Prize is a partnership between the Norwegian Academy of Science and Letters, the Kavli Foundation, and the Norwegian Ministry of Education and Research. The prize was initiated and funded by the late Mr. Fred Kavli, and is today being awarded for the 9th time.
Yes, and it really is a huge pleasure for us to be here in Oslo Concert Hall to present these fantastic awards. And I'm certain it will be an amazing ceremony. I mean, His Majesty the King is on the stage with us. Yes, this is my first, my first time doing this, but I'm glad I have you by my side. So honored. You've done this before, Jim.
The honor is all mine. I'm absolutely delighted to be back here in Oslo for this ceremony. And I'm sure we're all going to go away with being fulfilled and learning something new about the world.
Yes. Fred Kavli established the prize in Norway in order to recognize outstanding scientific research and to promote public understanding and support, of course, for scientists and their work.
The Kavli Prize really embodies Fred's own personal drive for increasing our understanding of the world, generating new knowledge, and striving for excellence. That, I believe, is something that all of us scientists try to do. After all, science at its very best not only uncovers nature's secrets, but also helps make our world a better place.
Yes. And Fred, he grew up in one of the most beautiful areas of Norway, a small village called Eresfjord. And this is on the magnificent northwest coast of Norway, near Åndalsnes. And I'm sure growing up in such spectacular surroundings would be both inspiring and help you contemplate the biggest questions.
I've never been there. I'd love to go. I hear it's a beautiful part of the world.
Yes.
One day, I'll make a trip there.
One day. We can go together because I haven't been there either.
There
but
we go.
Thanks to technology, we all can go to Eresfjord right now. You like it?
Quite breathtaking, actually. Yeah.
Yeah.
After all, we do have with us an extraordinary group of scientists. They may not want to do any base jumping, but their research achievements have been at the highest level. And I can promise you that we will all leave today a little wiser, knowing something new about our universe.
The Norwegian Academy of Science and Letters has established 3 international selection committees with members coming from France, United Kingdom, Germany, China, United States, and Norway. And these committees then recommend to the Academy who should receive the prize.
We should explain that it's the Norwegian Academy of Science and Letters that administers the Kavli Prize selection committees, the announcement of the Kavli Prize Laureates, and this Kavli Prize week in Oslo. The Norwegian Ministry of Education and Research and the Kavli Foundation, of course, are not themselves part of the laureate nomination or selection process. Each of the 3 prizes consists of a diploma, a gold medal, and $1 million. The first prize, will be in the category of astrophysics.
Yes, and I'm sure that Fred Kavli, as a little kid and probably as a grown-up too, looked up towards the sky and wondered what's out there. This was so beautiful. It's called Clair de Lune by Claude Debussy and was performed by the very talented Anais Grabowski, and she's only 14 years old. Yeah. Yeah.
See, that wasn't in our script to mention her age, but Selda said, shall I mention that? I said, yeah, I'm sure the audience are going to be impressed. It's remarkable. Well, we can all gaze up at the starry night sky with or without a telescope and wonder at our beautiful cosmos. The two laureates in Astrophysics 2024 spend their time trying to find planets where there is a potential for life, so-called exoplanets.
Yes, and exoplanets are planets orbiting sun-like stars in other solar systems, but in our galaxy. And there are billions of such solar systems just in the Milky Way.
And of course, they start their search in the nearest solar systems to ours. But it's not like they're just next door to us. We have tried to make a comparable example of how far away they really are.
Okay, listen to this. Standing at the surface of the Earth and watching an exoplanet in a nearby solar system, for example, the TRAPPIST-1 system, which is only about 300 trillion kilometers away, would be something like standing on the surface of the moon, trying to study a mosquito in front of the light of a lighthouse on the face of the Earth.
There we go. Perfect.
Yeah. It's hard to grasp.
It is hard to grasp. Well, the 2024 Kavli Prize in Astrophysics is awarded to Sarah Seeger and David Charbonneau for their groundbreaking work on the discovery and characterization of extrasolar planets and their atmospheres. So let's meet them.
Every society in history appears to have had astronomy as part of its culture. Today, astronomy, in the form of exoplanets, hopes to help us understand very basic questions. How did our Earth form and evolve? How did our solar system come to be? How did we come to be here?
Over the last 30 years, we've moved from discovering individual planets to really understanding the population and trying to put the solar system in context. Is the solar system a typical planetary system, or are we different in some way than the average planetary system? And the other big change is now we're able to really characterize these worlds. Okay, we don't just find one planet around one star, but there are stars where we know of 7 or 8 planets, and we can study the dynamics as these orbit each other.
Right now, one of the biggest topics in exoplanets is studying their atmospheres to get a clue on the interiors and what they're made of. And we're hoping that in the next few years with the James Webb Space Telescope and with hundreds of people working on exoplanet atmospheres, that we'll be able to solve some of the mysteries of what planets are made of and even maybe how they formed.
If you want to choose a planet that you're going to focus on, of course, you want 2 things. You want to present a really exciting science question, and I think looking for whether there might be life on that planet is one of them. But also you need it to be very close by, because we need the star and the planet to be as bright as possible from our point of view. And so there's been this big push to try to find the very closest stars that have these potentially habitable planets.
They're really just in our own solar neighborhood. But in the ideal case, what we would do is we're looking at a rocky planet, first establish if it has an atmosphere or not. Next, establish if it has water vapor, which on a rocky planet would indicate a surface water ocean. And if those pan out, we would try to assess the inventory of gases, typically like molecular gases there, and to try to work out whether any of these are unusual and don't belong, and whether any of them might be attributed to life.
If a planet falls very far out of this idea of this water habitable zone, then we don't expect it to have liquid water, and we don't expect it to have life as we know it. Of course, nature has been incredibly inventive in terms of the diversity of formation of planetary systems. I imagine nature's equally creative in terms of the formation of life. And so there may be many forms of life that are very different than what we're used to in our own Earth. but we have to start with searching for life that we would be able to recognize.
This is an incredibly complicated endeavor. There's a lot of unknowns. Just imagine, like a point of light. Imagine we're looking at starlight filtered through a planet atmosphere, a planet we know nothing about. First, we're just trying to detect a signal, and next to trying to create a story around that of what it could be physically. In the next decade, we are doing our very best to identify habitable planets using the JWST.
I think one of the really exciting opportunities that astronomy presents is because stars are being born continuously in the galaxy, when we find our neighboring stars and their planets, we're actually seeing planetary systems like the solar system, but at different ages. We don't have to just theorize what did the solar system look like when it was formed 4.5 billion years ago. We can find a sun-like star that is newly formed and study it and say, oh wow, look, there's the physics, there's the chemistry that went on. We can test our models directly. Similarly, there's a lot of science fiction, a lot of imaginative thinking about what the Earth will look like in another few billion years. But the galaxy actually has planets that are twice the age of the Earth, and we can go and study them and see what does happen geophysically, what does happen to planetary atmospheres as these planetary systems continue to evolve with time.
The most mysterious kind of planet today is a planet that appears to be the most common type of planet in our galaxy, a planet 2 to 3 times the size of Earth, that is in between the size of Earth and the size of Neptune. We have nothing like it in our own solar system. And we don't really understand what are these planets made of? How did they form? Astronomers around the globe are unpacking this story right now.
When we first started studying exoplanet atmospheres, the first method was to let them pass in front of the star, and we would see the starlight go through. But what we want to also do is see the direct thermal radiation, the infrared light that the planet itself is emitting. Now the trick is, how do you do that, right? Because the planet and the star are both emitting light, and they're very close together. We don't get to take a picture usually with our telescopes. They're not powerful enough to separate those points of light. And so we realized there was an opportunity when the planet went behind the star. When the planet goes behind the star, you can take a very, very good measurement of the infrared light, and then you wait until the planet comes back in view and they're both available, and you subtract them and the star goes away. And then the light that's left over is the direct light emitted by the planet. And that's been tremendously powerful in terms of understanding the weather on planets. We can see, obviously, just like the Earth, right? They warm up during the daytime and then they cool off during the nighttime, but there's a lot of winds that carry that energy around and redistribute it. So now we can really do climate science on exoplanets, and that all started with these measurements of the thermal emission of light.
The search for signs of life on exoplanets is a generations-long search. We're just starting it now. We will find signs that will encourage us to keep the search going. We might not find anything definitive in the next few decades, but we will find some very, very interesting signs that will encourage us as a society to keep going.
Please welcome onto the stage Sarah Seeger and David Charbonneau.
Well, Selda, even though my own research specialism is in the quantum domain, not in astrophysics, certainly for me, and I think for most people, this possibility that there is life elsewhere is one of the most fascinating and biggest questions in science.
Yeah, I kind of hope that as long as you have a pulse, you have thought about that question before. But I also want to quote my favorite astrophysicist, Carl Sagan, and he said, "The universe is a pretty big place, and if it's just us, it seems like an awful waste of space." And I think he's very right. One of the things I appreciate about the Kavli Prizes is that they cover the full spectrum of science and research, from the vast expanse of outer space to the tiniest particles and the most intricate concepts. And now we're transitioning from the enormity of space to the realm of nanoscience, which I must add is incredibly complex as well.
In the last 2 decades, nanoscience has transformed medical technology by harnessing the power of synthetic nanoscale materials for biomedical applications.
Yeah, and I would say that this represents a fusion of our best traditional knowledge in medicine with the latest advancements in nanoscience technology. Wouldn't you agree, Jim?
Absolutely. So much of modern scientific research is interdisciplinary in nature, a fusion.
Yeah, and I'm glad you said that, because speaking of fusions, you are about to meet Ib and Axel, 2 of the leading young composers and musicians in the fusion of classical and tech music.
They will premiere this piece that they have composed themselves for all of you, but perhaps most specially for the 3 winners in the nanoscience category. It's called Catalysis.
Ladies and gentlemen, Ib Lauritz Jensen Smørås and Axel Rostam. Give them another round of applause, please.
You know, I have to say I'm frequently impressed with today's young generation. Gen Z, we now have Gen Alpha as well. Older generations, I'm at the tail end of the boomers. Unfortunately, I just snuck into the boomers. We're often concerned about the future and what we're leaving behind. But I think if it's in the hands of smart and talented young people like this, I think we have nothing to worry about. By the way, Selda, I am including you in that bracket of younger generation.
Oh, Jim, thank you. Yes, I paid him to say that because I'm pushing 40. But yeah, thank you for saying that. Anyways, among the three winners in the nanoscience category, it's a particular honor to have Robert Langer with us. Rightly considered a pioneer, his groundbreaking idea from around 40 years ago has paved the way for integrating synthetic nanoscale materials with biological functions.
This convergence has then led to significant progress in drug delivery, diagnostics, and therapeutic intervention. So let's hear what he has to say about his early days.
What inspired me to get involved in nanotechnology and biomedicine was that idea of creating tiny particles to study cancer initially. But over time, you know, I could see that having tiny particles could be important in medicine, you know, whether it be for drug delivery, that's the area that I certainly have worked the most in. But there are lots of challenges to making it happen. I mean, you'd have to, you know, get the right kinetics, you'd have to make it biocompatible, you'd have to make it last long enough. Sometimes you use a non-degradable polymer, sometimes you use a degradable polymer, sometimes you use a combination of lipids. All of those, though, sort of provide like a little wrapper around a molecule. Then you inject them into the body and they will deliver the molecule either by diffusion of the molecule out, or the material will dissolve, or it could be some combination of it. When I tried to come up with the earliest systems that could deliver large molecules, you know, I failed over and over again. I developed some very simple tests for studying them. I'd have these little gels, and I put enzymes as model marker molecules in the little particles. So what would happen, depending on the model molecule, which is an enzyme, you could get a color change in the gel, or you'd get it to be transparent, or something would happen to the gel. So I did these tests where I put little particles in the center of the gel and, you know, incubate it at 37 degrees and, you know, come back an hour later and see if there was a change. And what I noticed is, depending how I designed it, nothing happened, nothing ever came out. And that kept happening over and over and over again, hundreds of times with hundreds of different designs. One time I finally came up with one way of doing it, just a certain type of material, certain concentration, certain design. And it turned color after an hour, turned color after 5 hours, turned color after a day. And it kept doing that over 100 days. I don't know that that was a breakthrough moment, but it was a breakthrough 100 days or many days, because After failing for so long, then I finally would see these things change color, and I saw it with I had 3 different enzymes I was using. And over the years, not only myself, but many of my students and many other scientists and companies around the world kept improving on these approaches and making them better and better. This has led to all kinds of medical products, different microspheres or nanospheres that can deliver drugs to treat cancer, to treat mental health diseases, and much more recently, it's led to delivery systems for messenger RNA that can create COVID vaccines, and people are looking at this for treating cancer vaccines and many other diseases.
And we are talking about nano-sized particles here, and my physics degree was in nanoscience, but I want to test you a little bit, Jim. Can you explain to the audience how small these particles actually are?
Okay, I'll try. Well, a nanometer is 1/1,000,000th of a millimeter. That itself may be hard to imagine, so how about this?
Isn't it 1/100000th?
A billionth of a meter.
Oh, yeah.
I switched it in the script at the last minute to millimeter, because millimeters are already small. I don't know if it makes it any clearer at all. But if you imagine a nanometer-sized crystal compared to, say, an orange, then that would be the same as comparing the orange to the size of the Earth. There.
Yeah. Yeah, also mind-blowing, but pretty good. But they are very small. And following in Robert Langer's footsteps, Paul Alevisatos and Chad Merkin have added invaluable new technologies to this science, which have already and will continue to open new frontiers in personalized medicine. This means enhancing treatment effectiveness and paving the way for innovative diagnostic and therapeutic strategies that improve patient outcomes.
Their contributions have made it possible for us to see inside living cells using so-called quantum dots. Now, these are crystals at the nanoscale. Through specially created nanoparticles coated with DNA or RNA, we now have a revolutionary and highly accurate way of detecting diseases, leading to faster and more precise medical tests.
Yes. So let's meet Chad and Paul.
A quantum dot is a tiny crystal in which all the electrons hold the atoms together in bonds. Right there. And if you put some energy into it and excite an electron, it now comes loose from that one place inside the crystal, and it starts to move around. And the smaller the crystal, the faster it moves. And when that electron then falls back into the hole, it emits light, and the color of the light changes with the size of the crystal. The smaller the crystal, the higher the energy, the bluer the light. That object can be tuned very, very precisely to make different colors. One thing about the quantum dots is that it's possible to have a single way to put energy into quantum dots of many different sizes. Let's say you have an array of these dots, and each one can be excited at the same time, but then they'll emit their own individual color. That, it turns out, allows for massively parallel screening. It allows for the possibility of seeing many, many interactions all at once. And it turns out that's actually a very fundamental piece of how the design of personalized medicine works, is you need to be able to ask questions about many different types of interactions at the same time, and then you can optimize them more broadly. So the underlying technology has that broader connectivity. We were able to demonstrate that quantum dots could, for the first time, be used to be directed to specific locations in a biological specimen to enable improved imaging over what was possible before.
Spherical nucleic acids are a great example of the importance of nanotechnology. I think of one of the most important molecules ever discovered by scientists, ever synthesized by chemists, as DNA. If you take short snippets of DNA and rearrange them on a tiny little particle, a nanoparticle, made of anything, it will have new properties. And those properties derive from that structure that is characterized by a shell of a oligonucleotide surrounding a central particle core, a spherical nucleic acid. One of them is that nanogold is catalytic with respect to developing photographic developing solution, whereas bulk gold isn't. And so if I use spherical nucleic acid gold nanoparticle conjugates as labels, for example, in a chip-based assay for DNA, I get one level of signal because of the intense color of the nanogold, but I can raise that signal by flowing photographic solution over the chip, and anywhere where the particles are, I can deposit silver and amplify the signal by a factor of 100,000 in a few minutes. That's created the ability to create highly sensitive detection systems for DNA, some that don't require the use of PCR, which was a holy grail back in the early 2000s. We are right now trying to completely change the way vaccines are made. And I don't mean through mRNA vaccines. I mean change the way vaccines are developed, taking them up a notch way beyond what we've done with the mRNA vaccines to a level where we can, in a very modular way, make the most perfect vaccine for a given type of disease. Give it the greatest chance for efficacy and the greatest chance of treating the world at large.
Please welcome onto the stage Robert Langer, Paul Alivisatos, and Chad Merkin.
Nice.
That was very nice. Congratulations, gentlemen. Well, we have one award left, and that's in neuroscience. Selda, are you good at recognizing faces?
Is this a trick question where I should say, no, I'm more into people's personalities and how they look?
No, you know that's not what I mean.
No, but...
I'm going to test you, though.
Okay.
So I want you to take a look at this image behind us, going to appear on the screen. How many different faces do you see?
How long do we have?
Well, we don't have all day, so... Yeah,
okay, I should... I think some of them are the same person because there is a mole, but yeah, I don't know. Say 5, 7, 7.
7, okay.
7 people.
There are actually only 2 people.
No.
Here. So this test was conducted on two groups, English and Dutch. Both groups were shown 50 different pictures of just two members of their respective royal families. The British mostly guessed there were 7 or 8 different individuals, while the Dutch were more or less unanimous in agreement that the different pictures were of just the two individuals.
Okay, so what does that mean?
I don't know. Maybe your brain is somehow the brain region for recognizing familiar faces. The Dutch people have stored their memory of their royal family there. The Brits probably don't. Maybe your brain is more of a British brain than a Dutch brain.
Okay, I'll take that as a compliment, I guess. But the science behind this is very interesting, and we will learn more about it in a bit. But now it's time to talk about the musicians you all have met and listened to this afternoon. And they come from the Barratt Due Institute of Musicians and the Young Strings of Norway, led by artistic director Sun Mi-chung Barratt Due. And since 1927, Barratt Due Institute of Music has been a cornerstone of Norwegian musical life, nurturing generations of talents into exceptional performers and educators.
As Norway's only private classical music conservatoire, it's internationally acclaimed for its talent development. So in 2027, the Institute celebrates 100 years of excellence, with 135 staff and 450 students continuing its legacy on the global stage. They now will play for us Orawa, composed by Wojciech Kilar. so talented, so young. I think I'm in awe. I think we're all really privileged to be here today to hear them.
Yes.
Well, back to the neuroscience and the study of the most complex system in the known universe, the human brain. The 3 laureates of this year's Kavli Prize in Neuroscience are honored for their pioneering work in the discovery of a highly localized and specialized system for representation of faces in the human and non-human primate neocortex.
Yes, this is so interesting. Nancy Canwisher pioneered the establishment of the functional region of interest approach to localize the fusiform face area in humans using fMRI, which is a method that measures brain activity by detecting changes associated with blood flow. Now, Nancy was the first to develop and employ a paradigm to identify a region in the brain sensitive to faces in each person.
Well, Winrich Freiwald and Doris Tsao then built on Nancy's work and used functional MRI to localize similar face patches in macaque monkeys. Having localized these regions of the brain, they recorded signals from single neurons in each patch and showed that the overwhelming majority of visual responsive neurons in the largest of these brain areas were able to identify faces.
Yes, so let's meet them.
Functional magnetic resonance imaging, or functional MRI, is a hugely important tool for understanding the human brain because it gives us the highest spatial resolution of any method available non-invasively. So it gives us the finest grained spatial picture of the functional organization of the brain. Functional MRI uses changes in blood flow when neurons are active. So if a little patch of your brain, say right here, gets active, the neurons fire a lot. That's metabolically expensive, so you have to send extra blood flow to that patch of the brain. Just as if you get up and run around, you have to send more blood to your leg muscles to enable you to run. When more blood flow comes to a region of the brain, that changes the relative amounts of oxygenated and deoxygenated hemoglobin. Those 2 molecules are magnetically different in a way the MRI machine detects. So we look at activity with MRI during one condition, say when you're looking at faces, and we compare that to activity in another condition, say when you're looking at objects. And we ask of each little patch of the brain whether it produces a stronger response when you look at faces than objects. And when we do that, we find the fusiform face area that's right in there on the bottom surface of the brain above the cerebellum, which is this structure here. Once we found the face area, we went on to show a number of things. For example, that its activity is correlated with your awareness of a face. If you look at a stimulus and you see a face in it, then the signal's high. If you don't see a face in the very same image, the signal's low. We then showed that you can close your eyes and just imagine a face and turn on that region. And if you imagine something else, you turn on other parts of the brain. And so we proceeded with experiments like that that enabled us to characterize when it turns on and what kinds of tasks it's involved in. But eventually with humans, even though functional MRI is the highest resolution method we have in humans, we still have several 100,000 neurons in each 3-dimensional pixel or voxel. And that makes it very hard to precisely identify the neural code for faces in humans. And that's why I'm incredibly excited about the work that Doris and Winrich have done, because their work in monkeys enables them to go in, find that region, record from hundreds of neurons in that patch, and really characterize in detail the neural code.
We have worked on the brains of macaque monkeys, so-called old world species related to us with about 25 million years of evolution distance, because their brains are organized in very similar ways to those of us humans. The advantage of the macaque monkey over the human brain is that it's much more similar from one individual to the other. It is not quite as complex as the human brain, and it allows us to do these mechanistic studies that would not be possible to do in the human brain.
The macaque monkey has such a similar visual system to the human, but at the same time, it's experimentally tractable. So, we can go in and record from single neurons with an electrode. The major tool that you have to study the human brain is functional magnetic resonance imaging, which is measuring blood flow. And some people say that's the brain's plumbing. Whereas, the way the brain actually computes is through these tiny neurons. Studying the monkey lets us study the code that's used by these single neurons. And it turns out that neurons that are right next to each other, they can be measuring completely different features, for example, of a face. So it's really important to study the neural code at that level of resolution.
The face processing network consists of several very functionally specific brain regions who are specifically connected to each other. So in that sense, it's a small version of the brain as a whole. There's local information processing, but there's also crosstalk between the different nodes within this network. And that we believe is a fundamental function of the brain that we can now study in this reduced setting. We have discovered signals that are being sent backwards from the more high-level areas to the earlier areas, making predictions about what the next stimulus might be. And this is one very fundamental theory about brain function, predictive coding, is that for the brain to be efficient, it will want to make predictions about what is going to happen, and then confine its processing resources to the surprises that emerge that deviate from those expectations.
What we found was that there are these face areas and they form a network, but actually this entire region of the temporal lobe is organized into networks of patches, and there's neighboring networks that are processing other shapes through the same principles. So the big picture that we have now is that the temporal lobe is representing an entire object space, not just of faces, but of other types of objects as well. So we think that the face areas evolved on top of this, right? So you have this master map of all of objects, and then because faces are so important, you need to recognize the face of your mother and your friends and so on, the cells can then become specialized, for representing the fine differences in identity. And so that's how we think it develops, and also, I believe, how it evolved.
There are big individual differences in people's ability to recognize faces. The bottom 2% of normal people is so bad at recognizing faces that they routinely fail to recognize family members. And the top 2% is so good that they get jobs with spy agencies in London identifying faces, and they hide it from their friends because it seems creepy.
Our research relies on the combination of multiple technologies. So there's brain imaging, functional magnetic resonance imaging, which is now moving to higher and higher field strengths. This is going to be the greatest opportunity for us to make progress, really understanding how the organization of the brain and its function work together. So for example, we don't understand how the very clear structural specializations that exist in the human brain align with the functional specializations like the ones that we've discovered. There must be a mapping, but we don't know what this mapping is.
So what we're going after now is, what is the brain's code for the actual world? How does it create this model of the world and of 3D space and all the objects in this space? Our hypothesis is that there's this key step of segmentation and tracking that's responsible for organizing all of these pixels into discrete objects. And we think that's actually accomplished in a different part of the brain, in the parietal lobe. And so we're doing lots of recordings there. And I'm hoping that this will eventually tie back into our work on the face areas, where we can study, how does this process of organizing a scene interact with this process of labeling specific objects in the scene, which is what we think the temporal lobe and these face patches are doing.
Please welcome onto the stage Nancy Canwisher, Vinrik Freivolt, and Doris Tsao.
Well, we've been through all three categories now and met all our laureates, so we're coming close to the end of proceedings. But first, Selda,
Please welcome the President of the Norwegian Academy of Science and Letters, Lise Øverås.
Your Majesty, Excellencies, Minister, Mayor, Kavli Prize Laureates, and friends of science. This is a great day for science. Today we honor 8 exceptional and outstanding scientists. We live in a research community. As a research community, we have a particular responsibility for communicating new breakthroughs, but also for transforming this research into innovations and new solutions. To this end, our modern society depends on the intellectual capacity of researchers like this year's Kavli Prize Laureates. We depend on their basic research to find answers to the big questions. They represent creative thinking and hope in the face of threats to our health and safety. The scientific achievements we celebrate today would not have been possible without the power of modern technology. In 1675, Isaac Newton wrote a letter to Robert Hooke with the famous word, "If I have seen further than others, it is by standing on the shoulder of giants," emphasizing that scientific knowledge is a summation of one's current work applied to an existing body of knowledge. Today, we do not only celebrate outstanding scientific results, we also celebrate the human capacities of these brilliant researchers who have inspired us with their creativity, scientific rigor, ethical standard, strong-minded persistence, and will to do good. Reading the laureates' own accounts of their lives and careers, I was touched by their gratitude, respect, and love they expressed for their mentors, their research partners, and their families. Each of them tells a tale of how they were inspired, encouraged, and not least, trusted with time, funding, and freedom to pursue their research interest. Some of them had to overcome obstacles and resistance from parts of the academic community, but they persevered because they eventually met someone who believed in them. They describe how intersectional cooperation and different academic approaches have educated and inspired them through the years. Gratitude is a beautiful thing, and there is a lesson here. The Kavli Prize Laureate reminds us that scientific breakthroughs does not only originate in our brains. Our social and emotional experience are also crucial to our intellectual endeavors. Research is built on joint brainstorming and discussion, on exchange of resources, methodology, and technology. This would not have been possible without trust. If the trust between human beings evaporates, and if the public no longer trusts that science has their best interest at heart, technology and artificial intelligence cannot save the day and the future. The Kavli Prize rewards the greatest achievement in research in the field of astrophysics, nanoscience, and neuroscience to support basic science and foster international cooperation among scientists. For the execution of this vision, we depend on the thorough and highly competent work of the Kavli committees. Because of them, we can say that awarding the Kavli Prize is also a work of building trust in science. Although modern technology and artificial intelligence are fantastic tools, ultimately the human ability to incorporate ethical and social consideration in the assessment of research effort is something that we will always rely on. On behalf of the Norwegian Academy of Science and Letters and the other Kavli Prize partner, I extend my gratitude to the members of our 3 committees Thank you for investing your competence and scientific standing in this important work. And congratulations again to the Kavli Laureates of 2024. Your contributions represent hope for what humanity can accomplish today, tomorrow, and in the future. Thank you.
Thank you very much, Lisa. Well, the Kavli Foundation provides the award money and the gold medals for laureates and promotes them and their science. So to elaborate on the Kavli Foundation's vision in honoring scientific achievements, please welcome onto the stage the president of the Kavli Foundation, Cynthia Friend.
Your Majesty, Ministers, Excellencies, Kavli Laureates, and of course all of you honored guests. It's really a privilege to be here representing the Kavli Foundation and to be able to share with you the joy and celebration today. As I was just introduced, I'm Cynthia Friend. I'm the president of the Kavli Foundation, which is a US-based science philanthropy that supports fundamental research in the fields of astrophysics, nanoscience, neuroscience, and theoretical physics. Fred Kavli established the foundation nearly 25 years ago with the vision to support and advance basic science for the benefit of humanity, a really remarkable vision and mission. The Kavli Foundation manifests our support for basic science through an international network of 20 Kavli institutes at universities worldwide, including 7 of them outside of the US and 1 of them here in Norway at NTNU, the Kavli Institute for Systems Neuroscience. The foundation also identifies transformative opportunities for research that can potentially drive high-risk, high-reward research that might not otherwise be funded. Further, the foundation recognizes the important connection between science and society, and most recently, we're supporting inquiry into potential ethical implications of scientific discoveries through centers that we have funded for that purpose. And of course, as is already stated, together with our partners, the Norwegian Academy of Sciences and Letters and the Norwegian Ministry of Research and Higher Education, we honor scientists and their groundbreaking work through the Kavli Prize. 73 laureates have been awarded this honor, including those 8 today, since the inception of the prize. They comprise an exclusive society selected, as Lisa already said, by an independent jury of renowned scientists in each of their fields. These laureates represent the leading science in their field, and they've made unique and important contributions to humanity's growing knowledge in the fields of our choice. We support basic research because we believe these advances result in part from the investment and investigation decisions that far precede their ultimate benefits. The mission, funded by our benefactor, Fred Kavli, supporting basic science for the benefit of humanity, is never-ending and always emergent. The benefits of science and technology to humanity, just since our founding, have been profound. Indeed, the Kavli Foundation is about to celebrate its 25th anniversary in 2025, and over these 25 years, the world has dramatically changed. The world population has grown from roughly 6 billion to nearly 8 billion. World gross domestic product has almost tripled from $34 trillion to $100 trillion. World trade has grown from $6 trillion to approximately 30 million, a factor of 5. And global research and development has grown from $700 billion to $2.5 trillion over the same time period. These 25 years have been challenging and often fraught, but nevertheless, humanity's curiosity and the basic research it commands endures. The discoveries of the Kavli Prize Laureates that we honor today have shown that to be true time and time again. From the discovery and characterization of extraterrestrial planets, extrasolar planets, and their atmospheres, and to foundational research that integrates synthetic nanomaterials in biomedical systems, and of course, as we just heard, the localization of areas in the brain that are specialized for facial recognition and processing. Each of them has already had a lasting impact on our society, and I'm sure that will continue in the years to come. So it's a great pleasure to congratulate the 2024 class of Kavli Laureates. It's a pleasure to be here. I want to thank all of you for being here, but on behalf of everyone at the Kavli Foundation, I want to wholeheartedly thank Your Majesty, His Majesty the King, for being here at this ceremony, but also for your enduring commitment to science and for presenting the Kavli Prizes today to the laureates. Thank you.
Thank you, Cynthia. We're about to end the ceremony. It's been wonderful. And the last thing we will do is that you, ladies and gentlemen, will be seated and welcome on stage all the laureates for a final round of applause.
Come on up.
Ladies and gentlemen, please all rise for His Majesty, the King of Norway.